Cyclic codes. A cyclic code is a linear code that has the property that a cyclic shift on any of its code words produces another code word. It is also a linear code. The only difference between the linear code and cyclic code is that when we make a cyclic shift, and what is a cyclic shift, you will see that later on, but whenever we make a cyclic shift of in a code word, then it produces another valid code word, and the number of shifts which we make is not limited. I mean, it can be any number of shifts, and it can be either from the right hand side or from the left hand side. The cyclic shift may be leftwards or rightwards by any number of places. Let's see the example of 7,4 Hamming code for cyclic shift. Let's consider first 7,4 code word C is equal to 0001011 and apply one place leftward cyclic shift. So what is a cyclic shift? What we are doing is that simply that we first of all we will remove this MSB over here, this last bit, and we will shift all the bits in this place. So this place over here is empty, this place is empty, and we will move this 0 here at this place. And when we look at this one, after this cyclic shift, this is called leftwards cyclic shift. If we go through the code words, 7,4 code word set of code words, we find that this is another valid code word, which is C2. So now we see another example. Here we are making rightward cyclic shift of 3 bits, not 1 bit but 3 bits. First of all, this bit is removed, as you can see over here. Then this bit is removed, and then this bit is removed, and then the remaining bits are moved to the right hand side till the end, and then they are placed back one after the other. So the first, this one goes in and it will go up to here, it will come here, then this one will go and it will come here, and this 0 will come over here. So the after cyclic shift, the answer is 01100001, which is another code word. And if we go through the list of set of code words of 7,4 Hamming code, then we find that this is code word number 6. As you can see, this is C6, 01100001, and this C2 is 010110. Now, to elaborate this cyclic shift a little bit more, what we do is that first of all, just think of it as we have put 5 balls in a pipe, and we have numbered them as 1, 2, 3, 4 and 5. I remove the 5th ball from the pipe at the right hand side, and then I shift all the balls to the end, and after shifting these balls, I place back this ball back from this side over here. So this is called cyclic shift, but this is the cyclic shift of 1 bit, and this is rightward cyclic shift. Now if I want to do 2 bits cyclic shift, then what will I do? Then I will remove this one more ball out of it again, and then I will move all the balls over here, and I will place this ball again back from this side. So this shift has become like this: 4, 5, 1, 2, 3. So it is easy to understand. It is there is not much more difficult. Now, cyclic codes encoding and decoding is possible in the same way as for linear codes, that is using matrices. However, a polynomial representation of code words is more suitable for cyclic codes encoding and decoding. To perform cyclic encoding and decoding, we need to know polynomial addition, subtraction, multiplication and division. Therefore, we will learn polynomial algebra first. Polynomial equation. General form of a polynomial equation and bit word representation in polynomial form is given as below. A an n-bit word, that is an minus 1, an minus 2, an minus 3 up to a0, can be represented as p of x a n minus 1 x n minus 1 plus a n minus 2 x raised to power n minus 2 and a n minus 3 x raised to power n minus 3 and so on up to a0 x raised to the power 0. And since we know that any number raised to power 0 is equal to 1 and any number x1 is raised to power 1 is equal to x, so we have just rewritten the same equation over here. So what we are actually doing, we are just simply representing our number of bits in polynomial form, and to represent it the method is very simple. We just simply count the total number of bits, and then we start with the x raised to the power n minus 1. That is, for example, if we have got 4 bits over here, then the first power of x will be 3. If we have got 5 bits, then the first power of x will be 4, and if you have got 6 bits, then the first power of x will be 5, and so on. So p of x is equal to 1. So what will I do? I will just simply multiply this x of cube. This and we could have been 1 and 0, either of the two, but in this case, since I am representing this 1 0 1 1 in polynomial form, so the first over here is 1. So this 1 is multiplied by x raised to power 3. Why 3? Because we have this 3 comes from 4 minus 1. Then I will keep descending or decreasing the power of x and keep multiplying this each term of x with its corresponding bit. So this 0 is multiplied by x raised to power 2, and this 1 is multiplied by x raised to the power 1, and this one is multiplied by x raised to the power 0. Of course, x raised to the power 0 is equal to 1, so I have just written down 1 over here, and this term becomes 0 because 0 multiplied by x raised to the power 2 is equal to 0. So the polynomial term for this 1 0 1 1 is x cube plus x plus 1. So simply I have represented this 1 0 1 1 in polynomial form. Similarly, p of x for 1 0 1 1 0 0 1 1 1 0 0 1 is p of x is equal to, again the same procedure. Here the power of x is 8y because the total number of bits over here is 9. 1 2 3 4 5 6 7 8 9. So 9 minus 1 is equal to 8. I will start with x raised to the power 8, which is multiplied by 1, then 0 is multiplied by 7. As you can see, we are just simply decreasing the power of x. 8 7 6 5 4 3 2 1 and 0, and keep multiplying with its corresponding bit. So 1 is multiplied by x raised to power 8, 0 is multiplied by x raised to power 7, 0 is multiplied by x raised to power 6, and so on. The terms which are multiplied by 0 are eliminated because they are 0. We don't need to write them. So there are 4 terms like that: this one, this one, this one, and this one. So the resultant term is x raised to the power 8 plus x raised to the power 5 plus x raised to the power 4 plus x raised to the power 3 plus 1. Now polynomial addition and subtraction. We can add subtract two polynomial equations by adding subtracting the coefficients of the terms having same power, and rest of the terms are written as they are. But for binary addition subtraction, we use modulo 2 addition. In modulo 2 addition, subtraction is the same as addition. In modulo 2 addition, the terms having the same power of x will be cancelled. So what we'll do is simply, for example, I have got a term p1 of p1x is equal to x raised to the power 5 plus x raised to the power 4 plus x, and there is another term p2x which is equal to x raised to the power 3 plus x plus 1. So the terms which differ in power, they will be written as it is, and the terms which have the same power will be cancelled. So this x to the power 5 is in this term, but there is no x to the power over here, so it is written as it is. X to the power 4 over here, it is not in this term, it is written as it is. X, it is in this term, so this x is cancelled by this x, and it is not written over here. This x cube is written over here because it is not in this term, and this one. So this is how we add or subtract the modulo 2 polynomials. Polynomial multiplication. The product of two polynomial equations is achieved by determining the products of all the terms taken pairwise and then cancelling like terms. So it is the same process as we do in normal algebra, that we add the powers when we have the when we are multiplying the variable. So x to the power 5 is multiplied by this whole term, so x to the power 5 is multiplied by x to the power 3, so powers are added, so 5 plus 3 is equal to 8. Then x to the power 5 is multiplied by this x, the x to the power is equal to 6, and then x raised to the power 5. Then this x raised to the power 4 is multiplied by x raised to the power 3, which is x raised to the power 7, and x raised to the power 4 is multiplied by x, which is x raised to the power 5, and x raised to the power 4 is multiplied by 1, which is x raised to the power 4. X is multiplied by x raised to the power 3, which is x gives x raised to the power 4. X is multiplied by x, which gives x raised to the power 2, and x is multiplied by 1, which gives x. So what we do is that we know that in modulo 2 addition, the like terms are cancelled. So x raised to the power 4 is cancelled by x raised to the power 4, and x raised to the power 5 is cancelled by x raised to the power 5. So the resultant or polynomial term is x raised to the power 8 plus x raised to the power 7 plus x raised to the power 6, x raised to the power 2, and plus x. Now when we are writing down that a polynomial term in a bit form, the simple thing is that we will write all the terms which are here as 1, and the terms which are absent will be written as 0. So x raised to the power 8 is 1, this 7 is 1, this 6 is 1, x to the power 5 is missing, so it is written as 0. X to the power 4, it's not there, so it is also written 0. X to the power 3, it's not there, it is written as 0. X to the power 2 is there, so it is written as 1. X is there, it is written as 1, and there is x to the power 0 or constant is absent, so it is written as 0. Now this polynomial division is the most important part of it, because this is going to be used for the to find the code word using polynomial generator. So we have to understand this polynomial division more thoroughly. The method of polynomial division is as same as the normal division method. Keep dividing until remainder is less than divisor. This term is called divisor. So let P1 x is equal to x5 plus x4 plus x, which is called dividend as well, is divided by P2 x, which is equal to x raised to the power 3 plus x plus 1, which is called divisor. So how do we divide it? First of all, we write this term over here and this x5 plus x4 plus x over here, and we look at the power over here. What we want such a term over here in the over here, which has got the same power. How do we get the same power of x to the power 5? By multiplying with such a value which gives us x raised to the power 5. That value is x raised to the power 2, because when x raised to the power 2 is multiplied by x raised to the power 3, the powers are added, and 3 plus 2 is equal to 5. So it gives me x raised to the power 5 over here. When this term x raised to the power 2 is multiplied by x, it gives me x raised to the power 3, because 1 plus 2 is equal to 3, and this x raised to the power 2 multiplied by 1 gives x raised to the power 2. So we do the same thing. We add the terms and the like terms are cancelled. So x raised to the power 5 is cancelled by this x raised to the power 5, and the rest of the terms are written as they are. X to the power 4 plus x to the power 3 plus x raised to the power 2 and plus x. Now I want such a term over here which gives me x raised to the power 4, which is x, because this its power is 1. 1 plus 3 is equal to 4. So I get x raised to the power 4 over here, and then this one multiplied by this x, so it gives me x raised to the power 2, and x multiplied by 1 gives me x. Again the like terms are cancelled. X raised to the power 4 is cancelled by this x raised to the power 4. This x raised to the power 2 is cancelled by this x raised to the power 2, and this x is cancelled by x. So the only term which is left over here is x raised to the power 3. Now is x what I do, I have got this x raised to the power 3 over here, so I just simply multiply it by 1. By multiplying by 1 means the whole term will be written over here as it is, x raised to the power 3 plus x raised to the power 1 plus 1. So this x raised to the power 3 is cancelled by this one, so the remainder is x plus 1, and quotient is x square plus x plus 1. This is how we do the division. If the remainder is 0, then divisor is a factor of dividend, otherwise it is not a factor of the dividend. This is divisor and this is dividend. If I would have got this 0 over here, then I could have said that this term is a factor of this term. But since I don't get a 0 over here, this term is not a factor of this polynomial term. Generator polynomials. The generator polynomial is a polynomial which is used to create all the other code words for a particular code. For example, generator polynomial g of x for 7,4 code is g of x is equal to x3 plus x plus 1. It is same as a matrix. A matrix is used to generate the code words. Here we are using a polynomial to generate the code words. Since this polynomial is generating the code words, it is called generator polynomial. And that polynomial is x raised to power 3 plus x plus 1 for 7,4 code word. The generator polynomial is unique within the code. So this polynomial is unique. As we have seen that this x raised to power 3 plus x plus 1 is nothing but actually it is simply this 1011. This 1011 is represented as x raised to power 3 plus x plus 1. So this form of bits, or this sequence of bits, is actually a polynomial generator. We have written this 1011 in polynomial form only. Now, how this is used to generate polynomial, to generate a code word, we have to see. Now, these all steps are for systematic code word only. For non-systematic code words, we don't need to follow these steps. Given an n, k cyclic code with generator polynomial g of x, an information polynomial ix is encoded into a systematic code word using the following step. First of all, I will multiply the information polynomial. So here we have to keep in mind that we have to convert the received code word into polynomial first. So this multiplied by not the received one, but the information bits which we want to encode are converted to polynomial form, and then they are multiplied by x raised to power n minus k. As we know that n minus k is the number of parity bits which are to be used in that coding. So for this is actually number of parity bits over here, n minus k. Divide the result of the first step by g of x to give the remainder r of x. Add r of x to the result of the first step to give the code word c of x is equal to I of x and x n minus k plus r of x. So what we will do is simply write them together, and but before we will multiply this I of x by n of x n minus k, which we already have done over here in the first step. Now let's see an example. Let's generate C10 of x and C12 of x code words for 7,4 code word. So for suppose I10 is I10 of x is equal to 1001. When we convert it into form of polynomial, 1 is multiplied by x cube. Why x cube? Because here we have got 4 bits. So 4 minus 1 is equal to 3. So 1 multiplied by x cube, then 0 is multiplied by x squared, then 0 multiplied by x plus 1, and that gives x cube plus 1. Now as we know that we have to multiply this term which we have got, this polynomial over here, which is to be multiplied by n minus k, x raised to power n minus k, which is x raised to power 3. So this term x cube plus 1 is multiplied by x3, which is equal to x6 plus x cube. Divide x6 plus x cube by g of x, now which is a polynomial generator for 7,4 code. So x6 plus x cube is divided by x cube plus x plus 1. We will do it again the same steps. First of all, we want a term over here which is x raised to power 6, and for that we multiply this term by x cube. When this 3 is x cube is multiplied by this x cube, it gives x raised to power 6, and then x cube is multiplied by x, which gives x raised to the power 4. 3 plus 1 is equal to 4, and x cube is multiplied by 1 gives x raised to power 3. Since x raised to power 3 and x raised to the power 6 are cancelled, the answer is x raised to the power 4. Again we divide it by x only, because x multiplied by x raised to power 3 is equal to x raised to power 4. X raised to power 4 plus x raised to power 2 for this term, x into x is equal to x square, plus x into 1 is equal to x. So this x4 is cancelled by the x raised to power 4 over here, and x square plus x is the remainder. Now the third step over here is that add rx to the result of the first step to give the code word. This is the first step. So in the first step, what we had multiplied this x cube by x cube plus 1. So what we will do is that we will just concatenate or add this remainder with this term. So x6 plus x cube as written as it was multiplied, and x square plus x is added to it. And after that we will just convert it into the bit form. As we know that since this should start from x raised to the power 6, why? Because the code word length is 7. So 7 minus 1 is equal to 6. So the first term is 1. Then x raised to the power 5 is absent, so it is 0. X raised to the power 4 is also not there, so it is also 0. But x raised to the power 3 is there, so it is 1. X raised to the power 2 is there, it is 1. X is there is 1, and x raised to the power 0 is absent, so it is 0. So this is the code word which is generated by this polynomial generator. For information code for information bits 1001. Now for information bits 1110, the same procedure is followed. Again, we first of all will convert the this 1110 in the polynomial form, which is x cube plus x square plus x, then multiply it by x cube, and the result is x raised to the power 6 plus x raised to the power 5 plus x raised to the power 4. And then we have to divide this term by x cube plus x plus 1. Again, the same procedure of division is followed, and the remainder over here is x square. This x square is written along with this term. So the resultant term is x6 plus x5 plus x4 plus x square, and after converting it into the bit form, it is 110100. Non-systematic cyclic code. If information polynomial is simply multiplied by g of x, then it produces non-systematic cyclic code. As you can see over here, there is another example. Here the same information bit 0111 is just simply multiplied by g of x, which is x cube plus x plus 1, and the resultant polynomial is x raised to the power 5 plus x raised to the power 4 plus 1. So the code word is 011001. This is a non-systematic code. So this shows that all the procedure, all the steps of multiplying and division, what we are doing over here is only to make the code word systematic. Otherwise it is not required. Otherwise, if we just simply multiply the polynomial generator with the information bits, then we will get a valid code word. But that valid code word will be non-systematic. It will not be a systematic code word. This step of multiplying it with the x of cube and then dividing it, then dividing that resultant with this polynomial generator gives us a systematic code word. Decoding cyclic code. For decoding, first of all, we need error syndrome. Error syndrome is constructed by dividing the error polynomial by g of x, and the remainder is the error syndrome polynomial. For example, if this is the e which we are going to use, then here, as we can see, the total number of bits is 1 2 3 4 5 6 7. So the maximum power is 7 minus 1 is equal to 6. So this x raised to the power 6, and this is x raised to the power 5. As we know that the terms which are 0 are not written, so x raised to the power is the polynomial for this error. And this x raised to the power 5 is simply divided by the polynomial generator again, and we get the remainder over here, this one, x raised to the power 2 plus x plus 1. So this is the error syndrome for this error. So if we get this remainder when we are decoding the received polynomial, and if we get this remainder, then it means the error is at x raised to the power 5, or the 5th bit of the 6th bit of the received code word. We can construct the whole syndrome table in the same fashion, and these are this whole syndrome table is constructed in the same manner as we by dividing the polynomial of error by x raised to the power 3 plus x plus 1. In order to decode the received code word, we simply divide it by g of x. It must give 0 in remainder if there is no error in the received code word, otherwise it will give error syndrome in the remainder.